History of Vector Analysis, Episode 10, Quaternions and Rotations. You are here. Hey, it's old Doc Euler. Welcome back. This episode is a change of pace. It's not historical. It's about one of the most important ways that quaternions are used today for modeling 3D rotations using digital processors. You may recall from a few episodes back that the mathematical world was set a Twitter by Wessel and or Gauss showing that multiplication by a complex number was analogous to a rotation in the complex plane. This had proven to have many practical applications as well as theoretical implications, so the question arises, does quaternion multiplication offer any similar practical advantages? William Rowan Hamilton, the inventor/discoverer of quaternions, had this geometric interpretation, which I showed earlier. His vision was that applying the I operator to a unit quaternion along the j-axis would rotate it onto the k-axis, and so on for the j and k operators. Does this generalize? Unfortunately, the answer is not really, unless you can think in 4D. Recall from the previous episode that when we multiplied two of those special zero real quaternions with the scalar part set to 0, we found that the resulting product was a quaternion with a non-zero component. Okay? This implies that in addition to rotation, multiplying one quaternion by another, even one that had no scalar component at all, still stretched the product in some way. Rotation and scaling are tied together in 4D in quaternions. That is, general multiplication of one quaternion by another does not have a simple 3D rotate and scale interpretation. Having said that, there is a remarkably great video by 3 Blue 1 Brown that presents what is probably the best visualization of quaternion multiplication that is even possible. Here's the link, but it should come up if you Google Visualizing Quaternions, the title. If you want to try your hand at understanding the problems associated with conceptualizing 4D, this is a great place to go. Still, we can imagine that there is an operator of some form that rotates a zero real quaternion into another zero real quaternion of the same overall magnitude. Such an operator could prove useful for 3D calculations, not just those crazy 4D ones. It would correspond to a pure rotation, either of something like a modern 3D vector or of a 3D coordinate system. So, does such an operator exist? And if so, what does it look like? Okay, a brief aside. This would be a nice place to introduce the concept of the 3D vector v instead of the 4D quaternion q0 that happens to have one of its 4 parameters set to 0. I'm not ready to do that yet, though, because the modern use of the term vector implies that the axes are real, not imaginary. So I will continue to use my own personal definition of q0 for the time being. Well, of course, I wouldn't pose a question like this if the answer wasn't yes. I'm not going to derive the operator, which would be messy and time-consuming if I could do it at all. Instead, I am simply going to state what the rotation operator R is and then demonstrate that it works. I begin by identifying the target zero real quaternion, the one we want to rotate, as q0 equals 0 plus ix plus jy plus kz. I use xyz here to identify it as the vector, in quotes, that we want to rotate. If q0 prime is a rotated vector of the same magnitude as q0, then R is the operator that we seek. Okay, nothing up my sleeve. From out of the blue, I will define a full 4D quaternion R for rotation, that has in general a non-zero real component. The values of the parameters will dictate the rotation, but I'm just going to keep it general for now. Okay, then I will use the rule we established in an earlier episode to define R inverse. Here it is. Finally, I state the answer. The rotation operator R is a triple product of R, Q0, and inverse R. Okay, if this operator resembles something you've seen in quantum mechanics, it's not a coincidence, but that is a tale for another time. Before I get into the proof, I want to point out a subtlety of the math here. We showed earlier that all quaternion multiplication is associative, so that we can write RQ, R inverse without ambiguity. You can evaluate this from the left or the right, and you would get the same result either way. However, we also showed earlier that quaternion multiplication is not commutative. Interestingly, at least I think it's interesting, the rotation operator would not work if the quaternion multiplication was commutative. You can see this as follows. Here's our expression. If we apply the associative property, we can clamp parentheses around the two right terms. Then we add the commutative property. If it were to be considered valid, we could swap the order of these two terms into this. Okay, then we use the associative property again and we move the parentheses here, but now we end up with r times r inverse, and we know that this is equal to unity. So in fact, all this does then, if the commutative property holds, is the rotation operator simply becomes multiplying by 1. Thus, we have found an example of something positive that results from the absence of the commutative property. How about that? Quantum mechanics, by the way, depends on the absence of this commutative property of multiplication all the time. Quantum mechanics doesn't work if, say, the position and the momentum operators commute. Okay, what does that say about external reality? Nope, I'm not going there. Time to wade into the math. Ready? Using our tiny font size again, all the charts are on the web. Let's go. I define Q0, R, and R inverse. To save a little space, I define kappa as the reciprocal of the magnitude of R inverse times R inverse star, which is a pure real number. In practice, problems like this are usually pre-configured so that the magnitude of the rotation operator can be taken as unity, so kappa will be unity, but I will include it here as a factor to maintain some generality. Note that, again, I am using XYZ instead of BCD to identify the object that we want to rotate. So our task is to evaluate RQ0 R inverse, which we know can be approached from either side via the fact that quaternions are associative under multiplication. I will choose to begin with RQ0 and then multiply from the right by R inverse after that. So here is RQ0. Note the choice of XYZ here on the right. For clarity, I form all 16 terms, 4 of which are 0. Then I evaluate the IJKs, and then I regroup by type, real, I, J, and K. Now for the next step. I multiply from the right by R inverse, pulling the real coefficient kappa out for some slight clarification. This yields 64 terms, but only 48 of them are non-zero. Whew. I used copy and paste to move the last expression to the top of the new slide for clarity. As usual, the next step is to evaluate the IJK terms and then regroup by coefficient. Copy and paste again. Now, I regroup in a new and different way. Note that each term in each line contains 2 sub-r coefficients, one from the rotation operator and one from the inverse, and then a third non-subscripted coefficient from the Q0, which I named X, Y, and Z earlier. Each of these 4 groups, the real, the I, the J, and the K, contain 12 terms. Of these 12 terms, 4 contain an X coefficient, 4 contain a Y, and 4 contain a Z. So within each line, I group by X, Y, and Z, and then pull these outside of another set of parentheses. And you can see here I got an X and a Y and a Z in each line. This, finally, is the payoff. Note that in the first row, corresponding to the real terms, each of the 3 XYZ sets cancels itself out, sums to 0. The real part of RQ0, R inverse, vanishes. And, just as impressively, note that the corresponding terms in the IJK rows do not sum to 0. Due to the nature of the cyclic and anti-cyclic computations, many of the terms actually double rather than vanish. The result is this. RQ0 R inverse equals the sum of these 9 terms, of which 3 are I terms, 3 are J terms, and 3 are K terms, and, here's the kicker, 0 real terms. To save a bit of time, I will simply tell you that the magnitude of RQ0 R inverse is the same as the magnitude of Q0. This tells us that RQ0 R inverse is a rotated version of the real-less quaternion Q0. How about that? Copy and paste again with the small addition of this here at the end to indicate that we have arrived at our destination. We can state that this equals this. Using modern techniques unavailable to guys like Hamilton, we can express this equation in matrix form. Q0 prime equals R, Q0, R inverse equals MQ, where M is equal to this 3 by 3, not 4 by 4 matrix. Note that the 4 ABCD coefficients are all from the rotation quaternion, and they are all real, as is the real coefficient kappa. As noted, the rotation quaternion is generally created in such a way that kappa is set equal to 1. As you may know, there are ways to create a rotation matrix without the use of quaternions. The standard technique used by physicists and engineers for decades is the use of Euler angles, the yaw, pitch, and roll translations used in physical navigation systems. This purely vector-based 3D approach works fine, at least most of the time, although you do have to watch out for the dreaded gimbal lock. You do not need quaternions to model 3D rotations. So why use them? Here is a comparison of the 3x3 rotation matrices using each approach. If you compare the two matrices, one does not appear to be simpler to evaluate than the other. So, why have quaternions become so popular recently for everything from physical navigation devices to software programs such as Minecraft that let you look in any direction simply by moving the mouse? Okay, it is true that if you were to calculate out a rotation matrix on your own by hand with the aid of a handheld calculator that does trig functions, the quaternion approach offers little, if any, advantage. The trick is to recognize that while digital electronics are good at performing multiplications directly, they are not as good at evaluating trig functions like sines and cosines. There are various ways to actually implement the cosine algorithm, but most simple variants are simple variants on the Taylor expansion as seen down here. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc. etc. You got to use a bunch of terms. That is, each matrix element in the Euler angle approach requires digital electronics to perform many more multiplications than the corresponding element in the quaternion approach. So, especially when graphics is involved, often with literally millions of pixels being reevaluated 30 or 60 times per second, the advantage of the quaternion approach becomes quite significant. Okay, the aim of this episode was to give you a practical example of quaternion methods that are in use today. I want to point out that I did not show you how to actually calculate a 4D rotation quaternion R based on a desired 3D rotation or a 2D mouse input. But I hope that this episode conveyed some context regarding the nature of quaternion math. In the next episode, we'll return to the history of vector analysis. This will involve some of the great minds that argued for and against Hamilton's quaternion approach, mostly after his death in 1865. In particular, I will discuss Peter Guthrie Tait, who developed the del operator. He didn't invent it, but he developed it, and used it to demonstrate some practical applications of quaternion math. It was Tait who introduced quaternions to James Clerk Maxwell, who, by the way, never actually wrote Maxwell's equations in their current form because that form didn't exist. Okay, that's next time. See you then.